Welcome everyone to our podcast on securing LLM agents against prompt injection attacks. Today we're diving deep into design patterns that could revolutionize both our technical and business strategies.
Thanks for having us. I'm particularly excited about how these design patterns, like the action selector and plan then execute, are already being adapted in real-world business scenarios. For instance, in customer service chatbots that are reinventing how companies secure sensitive data.
Absolutely, and technically speaking, the action selector pattern acts like a sophisticated switch. Only predefined actions are allowed, which keeps attackers at bay, much like how a well-configured firewall limits unexpected network traffic.
Right, and to add on, the plan then execute pattern is particularly interesting because it enforces control flow integrity by predefining a strict list of operations before any untrusted output can interact with system tools. Almost like a carefully scripted play where every line is pre-approved.
That's a great point, but from a business lens, this approach not only bolsters security, but also builds trust with end users. Think about a large retail company that saw a 15% cost reduction after integrating secure LLM agents in their operations.
Exactly, and we're seeing this across many domains: email assistants, SQL agents, even operating system helpers. And companies are realizing that secure design patterns are not just technical fascinations, but strategic investments in risk mitigation.
Ooh, excellent insights. Can someone explain a bit more about the dual LLM pattern and how it might practically shield critical functions from prompt injections?
Sure, the dual LLM pattern splits responsibilities between a privileged LLM that plans actions and a quarantined LLM that processes untrusted inputs without having tool access. This separation is analogous to having a secure vault where only indirectly referenced data is ever processed.
To dive deeper, the quarantined LLM outputs structured symbolic responses, which are then safely interpreted by the privileged LLM, ensuring that even if an injection happens, it's contained and cannot cascade into harmful actions. Think of it as a series of safety locks.
And for business leaders, this containment strategy means that even if an attacker attempts to manipulate inputs, say in a customer service chatbot, they're limited to a specific, non-harmful outcome, preserving both data integrity and brand reputation.
Building on that, real-world case studies like those in secure OS assistants show that isolating file actions via a MapReduce style, where each file is independently processed, drastically minimizes attack surfaces, similar to diversifying assets to reduce overall risk.
I'd add that this isn't just a theoretical framework. Companies making these design changes have reported fewer breaches and more agile compliance processes, which is huge when regulatory pressure is mounting in industries like finance and healthcare.
Fascinating. Let's talk about the code then execute pattern. How does this pattern elevate security without sacrificing the LLM's utility?
The code then execute pattern is where the LLM drafts a formal program that outlines the execution steps, and then this code is safely sandboxed. It's like writing a contract that specifies actions, so even if someone injects malicious commands, the code won't execute unless it passes validation.
Exactly. And technical validation here involves strict formatting rules, similar to JSON schemas, that ensure any dynamically generated code adheres to preset norms, thereby preventing injection attacks from morphing code unpredictably.
From a business perspective, this level of control is a game changer. For example, in SQL agents used for data analytics, companies can automate queries without fear that an injected prompt alters sensitive database operations.
That's right. The business risk is significant when sensitive financial or personal data is at stake. By sandboxing these actions, businesses can confidently automate processes without the costly overhead of manual approvals every time.
And let me throw an unexpected twist in here, a contrarian view. While many focus solely on efficiency gains, one might argue that the real bottleneck is not technical complexity, but the human element in verifying automated outputs, which is often underestimated.
Interesting point. you mean that the human oversight could either be a safeguard or a vulnerability, depending on how well it's integrated.
Precisely. The interplay between user confirmation and automated guardrails sometimes creates friction, but with the right design, such as context minimization techniques, we can essentially reset the slate after critical operations to prevent lingering injections.
Touching on context minimization, it ensures that once a user's prompt has triggered an action, it's stripped out from the subsequent operational context, mitigating the risk of reintroducing malicious code later in the dialogue.
And technically, you can view this as a kind of ephemeral memory scenario, where sensitive prompt data is removed on the fly, almost like clearing cache to prevent data leakage, which is a common best practice in secure software design.
In fact, during a project at a major tech firm, applying context minimization reduced the incidence of message tampering by over 80%, showcasing that even subtle design choices can deliver massive improvements in operational security.
I recall reading a famous quote, "The devil is in the details," and in this case, it's absolutely valid. The minor choices in design, like enforcing strict output formatting, make all the difference in real-world applications.
This is all incredibly insightful. Could someone elaborate on the challenges of deploying these patterns in a live environment, especially regarding scalability and integration with legacy systems?
Scalability is a non-trivial challenge. Integrating these patterns often means re-architecting parts of the system. Adding layers like the dual LLM requires orchestration components that must handle increased latency and resource overhead.
True, but remember, the 80-20 rule applies here. By focusing on securing the 20% most vulnerable vectors, you mitigate 80% of potential risks. It's a trade-off that most enterprise systems will find acceptable over a strict all-or-nothing approach.
From a strategic standpoint, businesses are already transitioning to modular architectures and microservices, which lends itself well to these patterns, allowing individual components to be independently secured and scaled.
I'd also point out that many legacy systems can be retrofitted with secure wrappers. Imagine putting an extra security gate in front of an old bank vault that already has defenses but now gets an updated lock system.
Definitely. And while some might worry about cost, remember that the expense of a security breach often far exceeds the investment in these design patterns. Shielding against data exfiltration is priceless in today's regulatory landscape.
That's a compelling argument. Now, how does the LLM MapReduce pattern assist in processing untrusted data without compromising the overall system integrity?
The MapReduce pattern divides the workload by dispatching isolated LLM subagents to handle individual untrusted inputs independently, ensuring that any malicious prompt in one segment doesn't affect the aggregate result. Very much like dividing a risk portfolio.
Technically, this means that each map function operates in a highly constrained environment, with its output rigorously validated before it's fed into the reduce phase. It's a microcosm of distributed security applied at the language model level.
And in industries such as finance, this means that even if a single data feed attempts an injection, it's isolated and cannot corrupt the overall decision-making process. For instance, in fraud detection systems where accuracy is paramount.
Businesses are taking note. In fact, a recent case involved a healthcare provider that used MapReduce patterns to secure patient data analysis pipelines, effectively limiting the impact of any single point of failure.
I'd like to add a nuance here. As one expert mentioned earlier, the human element is crucial. Automation is powerful, but we must ensure that our models are interpretable so that when anomalies occur, operators can rapidly understand and intervene.
Absolutely. It's like having a well-trained pilot monitoring an advanced autopilot system. Trust but verify remains the mantra.
Well said. The combination of robust design patterns and vigilant monitoring creates a layered defense, which is essential given that no single technique is infallible.
And to echo that, continuous evaluation is necessary. Just as cyber threats evolve, so too must our security patterns. with periodic reviews and updates, ensuring that these agents remain resilient in the face of new attack vectors.
I agree entirely. Regular security audits and simulation tests, similar to fire drills in physical security, become part of best practices for business continuity in tech-driven companies.
And remember, sometimes simplicity trumps complexity. Often the simplest design decisions, like removing untrusted context immediately after use, have the biggest impact in reducing vulnerabilities.
That's true. As a famous saying goes, keep it simple, stupid. Complexity is the enemy of security.
Wonderful discussion, everyone. As we wrap up, could each of you give a final takeaway for our audience?
My key takeaway is that secure design patterns for LLM agents are not just an academic exercise. They're vital for building trust in technology, protecting both data and reputation in the business world.
From my perspective, the technical innovations we discussed, particularly the dual LLM and code then execute patterns, provide robust frameworks that push the boundaries of what's possible in AI security.
I'd say that our deep dive reveals how essential it is to embed security at the system design level, not as an afterthought. Solid architecture can diffuse many advanced threats before they even emerge.
Strategically, companies should view these patterns as investments in long-term resilience. The costs saved from preventing breaches or data leaks are immeasurable in today's market landscape.
Finally, always remember that blending technical rigor with business insight creates a powerful synergy. Secure AI isn't just about stopping attacks, it's about empowering innovation with confidence.
Thanks to all our experts for this engaging and enlightening discussion. Your insights have truly bridged the gap between technical complexity and strategic business value.
Thank you. It's been a pleasure sharing these ideas and exploring how we can shape a safer AI future.
Yes, thanks for the great questions and the chance to deep dive into these fascinating patterns.
Really enjoyed this conversation. Let's keep pushing the envelope on AI security.
It's been a great session, and I'm excited about the future possibilities these design patterns will unlock.
Thank you, everyone. Here's to building smarter, more secure systems that drive business success.
And thanks to our listeners for tuning in today. Stay curious, stay secure, and we'll see you next time on our podcast. Welcome back to part 2 of our discussion. Now we're really digging into the technical implementation details that bring these design patterns to life in real-world systems.
Absolutely. Let's kick off with the action selector pattern. This design is implemented by hard-coding specific action templates, essentially creating a secure API layer where the LLM only maps input phrases to pre-approved commands, which is analogous to a command line interface with a fixed set of commands.
And from a technical standpoint, this means you'd use strict input validation and output filtering, often with regex-based sanitation and explicit tokenization, to ensure that the LLM cannot deviate from the predefined actions, thereby reducing the risk of unintended code execution.
Building on that, the plan then execute pattern introduces a 2-phase processing model, where the LLM first generates a detailed action plan that outlines the specific sequence of tool calls, and then a separate module verifies and executes each step, much like a transaction verification system in a banking application.
For business leaders, this separation means critical operations such as customer data processing or transaction auditing are less prone to errors or malicious alterations, making the entire system more reliable and predictable for high-stakes applications.
One technical nuance here is the use of strict interface contracts between different modules. The action plan is represented in a structured format, often JSON, to enforce consistency before any action is taken, resembling API schemas that ensure interoperability and security between services.
That's a great point. Speaking of structured outputs, can you explain how the code then execute pattern leverages code sandboxing in controlled execution environments?
Sure, in the code then execute pattern, the LLM is tasked with writing code, but before execution, This code passes through a sandbox environment that governs permissions and resource access. It's similar to deploying microservices in containerized environments where each service is isolated and monitored for abnormal behavior.
Technically, this involves using containerization tools, like Docker, with strict security profiles, and perhaps even employing static code analysis tools to inspect the generated code before it is run in production, ensuring that it adheres to the specified security guidelines.
And on the business side, this approach minimizes the risk of data leakage or unauthorized modifications in systems such as automated SQL agents or code assistants, where any injected code can be isolated and prevented from causing cascading failures in core systems.
Exactly. The dual LLM pattern, for example, splits functionality into a privileged LLM that directs actions and a quarantined LLM that processes untrusted inputs. And the key here is the orchestrator component that acts as the gatekeeper, converting symbolic responses into actual function calls without ever exposing sensitive data.
I find this model elegant because it mirrors the defense-in-depth strategy in cybersecurity, where even if one layer is breached, subsequent layers ensure that no harmful side effects occur. This layered architecture is something businesses appreciate when evaluating risk management strategies.
Let's talk about practical applications. How have these patterns been successfully integrated into live systems, and what are the common pitfalls to watch out for?
In live deployments, especially for systems like OS assistants and email calendars, engineers often use a MapReduce pattern to distribute the workload across multiple isolated LLM subagents. Each subagent processes a fragment of data independently, and their outputs are aggregated in a controlled manner to minimize risk.
A key pitfall, however, is ensuring that the orchestrator managing these subagents imposes strict validation rules. The aggregation step must filter out any anomalous outputs that could be the result of a prompt injection, which is often achieved by statistical anomaly detection algorithms.
An effective strategy here is to apply an 80-20 rule, focusing on securing the most vulnerable or high-risk data paths first, such as financial transactions or customer-sensitive data, while gradually extending the secure patterns to less critical modules over time.
From a business perspective, investing in modular security updates and regular system audits is crucial. Companies that retrofit legacy systems with wrappers that enforce these design patterns tend to see measurable improvements in operational integrity and customer trust.
And let me offer an unexpected twist. While many focus on tight security, sometimes adding too many layers can introduce latency or operational friction. The challenge is finding that optimal balance where technical robustness meets efficient user experience, which is where agile iterative testing really comes into play.
That's a fascinating insight. The balance between security and performance is critical, especially when scaling these solutions in a live business environment.
Precisely. Continuous monitoring and real-time logging are indispensable in live systems. Using tools like secure logging frameworks and intrusion detection systems allows you to catch potential injection attempts as they happen and adapt your guardrails accordingly.
Moreover, these technical deep dives are complemented by regular security drills, similar to fire drills in physical security, which simulate injection attacks to test the resilience of the LLM agent system, ensuring that both human operators and automated defenses remain responsive.
It's all about creating an ecosystem where the technology not only performs well under ideal conditions, but remains robust under attack, which is critical for high-value applications like healthcare diagnostics or financial data analysis.
And let's not forget, these technical measures have profound business implications. Reducing downtime, preventing reputational damage, and ensuring compliance with increasingly strict data protection regulations is a competitive differentiator in today's market.
In essence, implementing these secure design patterns is not just a technical exercise. They're strategic initiatives that protect the bottom line and enable innovation, ensuring that businesses can confidently harness the power of advanced AI agents.
Truly compelling. Thank you all for this technical deep dive that brilliantly bridges complex implementation details with clear business value. And thanks to our listeners for joining us on this journey into the heart of AI security. As we wrap up this deep dive, let's take a moment to summarize our journey. From design patterns like Action Selector and dual LLM architectures to the rigorous sandboxing and MapReduce strategies that secure our systems against prompt injections.
Right, the conversation illuminated how design patterns such as plan, then execute, and code, then execute not only provide technical safeguards, but also offer a scalable framework that businesses can trust, much like building a fortified bridge over turbulent data streams.
And from a technical perspective, our discussion underscored the importance of structured outputs, strict interface contracts, and isolation mechanisms. These are not just clever coding tricks, but fundamental building blocks for resilient AI systems in mission-critical environments.
Exactly. These patterns embody a defense-in-depth approach. By compartmentalizing risks and enforcing rigor at every layer, we're not only countering prompt injections, but also creating systems that can adapt and learn from potential threats, similar to regular fire drill scenarios in cybersecurity.
On the business front, the real-world case studies we touched on, from SQL agents automating financial queries to booking assistants and even resume screening tools, demonstrate that deploying these secure patterns can lead to measurable improvements in efficiency, customer confidence, and compliance with data protection regulations.
And here's an unexpected insight. While security is paramount, the balance with user experience and operational speed is equally critical. An optimal design minimizes friction without compromising safety, a principle that's as applicable in AI deployment as in any mature business strategy.
In summary, our conversation today provided an end-to-end view of how carefully engineered design patterns can mitigate the risks of prompt injection attacks, secure sensitive operations, and ultimately serve as strategic enablers for innovation in various industries.
We explored actionable methods like sandboxing, dual LLM deployments, and modular validation that not only protect our systems, but also enhance reliability and transparency in automated decision-making processes.
And by maintaining tight control over untrusted inputs through approaches like context minimization and strict symbolic data manipulation, we enable safer interactions between complex LLM agents and external data sources.
The take-home message is clear. The future of secure AI is in integrating these principled design patterns that allow both technical robustness and strategic agility, ensuring a win-win scenario for technology and business leaders alike.
I'd say this holistic view reminds us that innovation thrives when security and utility are viewed not as trade-offs, but as complementary drivers of success, echoing the zeitgeist of modern digital transformation.
Absolutely. By embedding security into the core architecture of our AI systems, we empower businesses to confidently ride the wave of automation and intelligent decision-making while keeping risks at bay.
Thank you all for these invaluable insights. It's been a compelling session that not only highlights the technical intricacies and real-world applications, but also reinforces the strategic importance of designing secure AI systems. Till next time, stay secure and keep innovating.